Okay, so now how can we approach the problem in a different way to eliminate dealing with all of those massive numbers that we already discussed? Well, we're going to use this theorem by Pierre de Fermat that says that any prime number, p, can be represented as the sum of two squares if and only if p takes the form of 4k plus 1, where k is some integer. And that's awesome because the prime numbers that this problem is having us consider are those prime numbers that take that form. So now we know that all of the prime numbers we are considering have exactly one unique way of being represented as the sum of two squares. An important consequence from this theorem is the Brahmagupta-Fibonacci identity, which in essence states that take any two numbers that can be both represented as the sum of two squares. This number is the sum of two squares, and this number is the sum of two squares. Then their product is also equal to the sum of two squares in two unique ways. You can find one unique way through this formula, where this value inside the parentheses would be an a, and this value could be b. And there's a second unique way just by flipping some of the flipping the sign in between the variables rather, where this would be a different a and this would be a different b. For example, let's consider the prime numbers 5 and 13, which can be both represented as the sum of two squares by the theorem, where 5 is 1 squared plus 2 squared, and 13 is 2 squared plus 3 squared. And their product is equal to 65. Since we expressed this product in this form, then we can use the identity, do some simplification inside the parentheses, and discover that there are two unique ways to represent 65 as the sum of two squares, like we already talked about, 8 and 1 or 4 and 7. This identity doesn't just hold when you're doing this with prime numbers, though. Actually, it works for any two numbers as long as they are both represented by the sum of two squares. Moreover, say one number has two different ways, like 65, two different ways to be represented as the sum of two squares. And say a second number has four unique ways that it can be represented as the sum of two squares. Then the product of those two numbers will actually have 16 unique ways that it can be represented as the sum of two squares. How so? Well, what you do is there are two different pairs of A and B for the first number and four different pairs of A and B for the second number. For each combination of a pair from the first number and a pair from the second number, you can use the identity and derive two new ways to represent their product as the sum of two squares. So we'll get two unique pairs from each of these pink lines that connect a pair from the first number to a pair from the second number. This is going to be a useful way to think about some of the larger numbers that we're encountering when we multiply a lot of these prime numbers together. Another key thing to note is that this formula has no dependence on n. Never in the calculations do we have to figure out what n is, take a square root or subtract or anything that might provide that extraneous source of error that we already discussed. So next, I'm going to describe how to use this identity to construct all of the pairs of A and B for all of these square-free numbers that are only divisible by the primes of this form and that are less than 150. Now is where it comes in that Java is an object-oriented programming language. What that means is that I'm able to design my own objects in Java that have different properties depending on what I am aiming to do. Specifically, I designed an object called a Fermat set, inspired by the theorem that we discussed by Pierre de Fermat. A Fermat set is meant to represent all of the A and B solutions for any value of n. For example, when n equaled 5, there's one solution. A equals 1, B equals 2. And a Fermat set has two arrays, an array of A values and an array of B values that were solutions. So when n equals 5, if we want to create that corresponding Fermat set, there will be one value in the array of A values, 1, and one value in the array of B values, 2. So how can I make a Fermat set? Well, I made two different ways that are going to be useful for us. The first is the simple one. Take some n value and run it through that naive algorithm that we already discussed, where you just brute force, check every combination of A and B, and see if you can find some solutions. That works really well if n is small, such as being one of these primes. The other way to make a Fermat set is used for those larger numbers. Specifically, what I do is I can pass in two other Fermat sets, and the result will be a Fermat set representing the product of the original two Fermat sets. It does this by using the previous identity to determine all of the A and B values for the new Fermat set. I also designed a helpful function that simply returns the sum of all of the A values for any Fermat set. This is exactly what the function s of n does, but instead of passing in an n, I pass in a Fermat set. This gives us all of the tools that we need to start solving this problem. So we need to systematically find every Fermat set for all square-free n that are only divisible by these primes. And I do this through a recursive method. Specifically, start at the first prime that we're concerning, 5, and we can make its Fermat set simply by using the first constructor. Then, add it to a list of Fermat sets. This list is what's going to hold eventually every single Fermat set for any n that we care about. After I add that Fermat set to the list, go to the next prime, 13, and create its Fermat set. After I created the Fermat set for 13, I want to create the Fermat sets for 13 combined with all previous Fermat sets that were in the list. So I use this second constructor, combine the Fermat sets for 13 and 5, and I'll get the Fermat set for 65. Add that to the list. I can keep repeating this process. So now go to 17, create its Fermat set, add it to the list, and then combine 17 with all previous Fermat sets. Combine it with 5, combine it with 13, and also combine it with 65. Eventually, once we get to 149, we will have in our list a Fermat set for every square-free n only divisible by these primes. Then, after we have every single Fermat set listed, all that's left to do is actually solve the problem. Call sum A on each Fermat set in the list, sum all of the different sums together. In doing so, you'll find that the final sum is roughly 2.0 times 10 to the 18. Of course, I'm not going to give you the actual answer. If you want to do that, go ahead and code it up yourself. I think it's a very rewarding problem, and I definitely learned a lot about Java and about general problem-solving techniques to this problem. Thank you.